Okay, so we've now introduced hidden Markov models, and in the previous section I gave basic definitions of those models. In this next section I want to talk about how these models are learned from a set of training examples, in particular how those Q and E parameters we saw, the trigram parameters and the emission parameters, can be estimated from a set of training examples. And this is actually quite straightforward. So let's take the Q parameters as a start, and let's say for example, we want to estimate the Q parameter corresponding to the probability of seeing this tag, VT, given that the previous two tags are these two tags here. And we can use our training corpus, of course, to induce counts of different tag sequences. So what I've shown you here is essentially a linear interpolation method for estimation, very similar to the methods we saw for trigram language models in the last lecture in this course. So here I have an ML estimate, maximum likelihood estimate. Actually, this is the trigram maximum likelihood estimate. And notice on the denominator, I have the number of times I've seen dt followed by jj. That's what we're conditioning on here. And on the numerator, I have the number of times I've seen this sequence of three tags. So this is the trigram count, this is the bigram count, and I've taken the ratio of these two terms. These counts can be taken directly from those training examples, which consist of entire sentences together with their part-of-speech sequences. Similarly here, I have a bigram maximum likelihood estimate. So again, it's a ratio of counts, number of times I've seen JJ, that's the second tag in this sequence we're conditioning on, and then on the numerator, the number of times I've seen JJ followed by VT. And finally, I have the unigram ML estimate. On the numerator is the number of times I've seen the tag VT, and on the denominator is the total number of tags I've seen in my entire training corpus. So we have a linear interpolation method, we have these three smoothing parameters, exactly the same as we saw for language modeling. These lambdas satisfy the constraints that they sum to 1, and they're all greater than or equal to 0, and they can be estimated from data in a very similar way, actually an identical way to what I showed you for the language modeling problem. So this is basically a direct application of the methods we saw for language modeling. Okay, so secondly, we've got to consider these emission parameters. For example, E of base given VT is the probability that the tag VT emits the word base. And again, we can derive maximum likelihood estimates that take a very intuitive form. So on the denominator, I have the number of times I've seen the tag VT. And on the numerator, I simply have the number of times that I've seen the tag VT paired with the word base, and we simply take the ratio of these two terms. So it's a blindingly simple estimate. So that's basically it, although there's one problem we need to worry about, and that's the following. So E of x given y is going to be 0 for all y if x is never seen in the training data. So what am I saying here? Basically saying for any word x that is never seen in the training data, we're going to estimate all of these emission parameters to be equal to 0. And in some sense, that means we have no useful information about that word. And this is actually going to be a real problem in these models, but I'll describe a simple solution to it. Why is this important? Let's come back to an example from before. And let's say, for the sake of argument, that this is a test sentence. And so I would apply my tagging model to this test sentence and try to find the most likely sequence of part-of-speech tags for that sentence. Then we're very likely in a given test sentence to encounter words which we've never seen before in training. So Mullally, for example, quite possibly has never been seen in our training data, or maybe even topping is a relatively infrequent word and may not have been seen in our training data. And actually, if you look at the statistics of English, for example, even with, say, 1 million words of training data for tagging, you will frequently encounter words in test data which you've never seen in training data. What that means is, let's take this particular example. So E of Mullally given Y is equal to 0 for all tags Y. And that means if this is defined as our sequence x1 through xn is equal to this, it's easily verified that P of x1, xn, y1 through yn plus 1 is equal to 0 for all tag sequences y1 to yn plus 1. And that's because any tag sequence is going to involve an emission parameter like this, which is equal to 0. And so all of these probabilities are going to be taken to be 0. And of course, at this point, the model is completely broken down because all of my tag sequences have probability 0. And in fact, if I think about trying to find the most likely tag sequence, or the argmax over all tag sequences of this expression, we just have a tie where all tag sequences get the same value of 0. Okay, so this model is broken, but there is a very simple fix. So a common method which is used is as follows. So in the first step, we split the vocabulary into 2 different sets. We'll do this as follows. I'll define so-called frequent words to be any word occurring greater than some threshold. So for example, a typical value might be 5. We define a frequent word to be any word occurring 5 times or more in training. And we define low frequency words to be all other words. So this is going to include words seen less than 5 times in the training data, and also words which are seen 0 times in the training data. So all those new words that we see on test data examples which have never been seen in training. So that's the first step. And the second step, we're going to define a mapping where we map low frequency words, so all the words in this set, into a small finite set, typically depending on spelling features of those words. I'll give an example of this in the next slide. But the basic idea is to take this very large set of low frequency words, there might be many, many words that fall into this class, and for each word just map it into one of, say, 10 or 20 new words, this small finite set. Let me be concrete by giving an example. And this is from a paper by Bickel and others from 1999, specifically on the problem of named entity recognition. So they defined a mapping from these low frequency words to roughly, I think there's roughly 10 or 15 different possible word classes. And these were chosen by hand and using some intuition and insight about the problem that they were attacking, which was named entity recognition. So this partition of the low frequency words into these different classes has been chosen to try to preserve some useful information in the named entity recognition task. So for example, if they see a low frequency word consisting of 2 digits, they map this to a class called 2-digit num. 4 digits, 4-digit num. Let's look at some others. A word which is all capitals gets mapped to a word called all caps. We have anything which is the first word of a sentence is mapped to a symbol called first word. That's essentially because even though that word is capitalized, the capitalization information is not that useful in that case, because all words at the start of a sentence are capitalized. Any word whose initial letter is capital, but whose other words are not capitalized, is mapped to inner cap, and so on and so on. So let's continue this example, and let's come back to, this is the original form of our training data. So again, I'm looking at the named entity problem here, and assume this is a training example where somebody has actually annotated the different entities in this particular example. So before the transformation, the data looks like this. But here's what the data looks like after the transformation. And there are a number of low-frequency words here which have been mapped to these kind of pseudo-words, these words in a small set of categories that preserve spelling features about the words. So profits is mapped to first word, Boeing is mapped to init cap, we have lowercase init cap, and so on and so on. So you as a human can look at this data, and you can see that even though we've discarded the precise identity of these words, we've still preserved quite a bit of information, and most importantly, information about the underlying spelling of those words, which will be useful in the named entity problem. Okay, so we perform this transformation to both our training examples and also our test examples, and then we simply build a hidden Markov model tagger using data in this format. So we now have parameters such as the probability of seeing first word, given that the tag is NA, or an emission parameter specifying the probability of seeing init cap, given that I have the tag SC, and so on and so on. So we've essentially finessed this problem of low-frequency words, or words in test data never seen in training, by closing the vocabulary, by mapping those low-frequency words to a much smaller set of 20 words which preserve information about the spellings. The nice thing about this is that it's a very simple method. Once we've done this, we can simply read off straightforward maximum likelihood estimates of these different parameters. The downside is that it's clearly heuristic in that some human expertise has to go into the design of this mapping to a small number of word classes.